Thank you
Thank
very
you.
much.
Thank you, sir. Thank you very much. Am I audible to everyone?
Yes,
Yes,
yes.
yes, yes. You're very much.
Okay, so, I'll begin. Basically, uh, this is a advanced level lecture talk, which is in continuation to the first lecture talk, which I had conducted last month. In the first lecture talk, we had covered the basic aspects of short pinning machine, and now we'll go a little bit in depth in the short pinning process and its theoretical and measurement part, basically. So we are going to talk to about basically first understanding the short pinning requirements. Then you have got what you can say the first major aspect, which is the saturation curve analysis. So I'll just briefly overview just to refresh the memories. I won't go in much depth. Then we'll look at the pinning media specifications and quality control. Later we'll jump into the theoretical part of the residual stresses and how they are measured. And lastly, we'll talk very briefly about optimizing the process and the practical troubleshootings that we have come across over the past many years. Okay, so like Rege sir said, we are into manufacturing of short pinning and short blasting machines. Uh, the company was started by my father in 1983, and since inception, we are into short pinning and short blasting machines. Uh, as being a very old company and driven by technocrat individuals, we have our own product development teams, and all the designs are developed in-house. And as such, we hold quite a few patents and design copyrights for our machines. So our main business, as I said, is into short pinning and short blasting equipments. Apart from that, we also provide what you can say consultancy services in terms of implementing the short pinning process, carrying out the audits, and also establishing the short pinning for various parts. Okay, now first we'll directly see what a typical requirement for short pinning process looks like. So generally speaking, uh, a client will give you a short pinning requirement, which will first see what you can call as the arc height, which is given in mm or inches. Followed by that, you'll see what type of strip, the grade of strip that needs to be used, N, A, or C. Then the pinning areas should be indicated under drawings. Generally speaking, the whole component is never short pinned. Only the critical areas like the gear area. Even in the gear area, you might have uh, say the root and the flank, which need short pinning. Then the most important part which the user has to see is if there's any masking required. Masking means the customer is suggesting, the client is suggesting that some areas should be protected from short pinning. So you have got various sacrificial layers available. You have got various tapes, stick on tapes. You can use metallic fixtures which are going to act as a protection barrier. If not, then there is no harm in pinning the entire component if it is getting exposed, because actually masking is going to add up to the operating cost rather than reducing it. After that, you'll come across the short pinning specifications. Now the short pinning, the short specifications. The short specifications means the size of the shots, the grade of the shots. There are three grades: grade 1, grade 2, and grade 3, depending on the sphericality of the shots. Then you have got the hardness and the chemical composition. After that, you'll come across the term coverage, which basically it is mentioned in percentage. So it might be written something coverage required is 100% or beyond 100%, say 150%, 200%. Requirement which we have reproduced here, obviously with the due consent. Now here you can see the arc height is given, which I had mentioned earlier. The arc height always is mentioned in a particular range. It is not never an absolute value. So in this particular case, it is 0.5 mm to 0.6 mm. And A strip is mentioned, so obviously we have to use the A strip. The short size mentioned is S230. 230 denotes the diameter of shots in thousandths of an inch. So it is 0.23, which roughly comes around 0.6 to 0.7 mm. Again, you have got various standards mentioned over here. The SIJ 444. Shot hardness is given and the coverage is mentioned. Now here you can see the coverage mentioned is 200%. We'll talk about this later when we go into the saturation curve analysis. And the residual stresses. Now here, most important point to observe is that what needs to be measured is the desired rise of compressive stress. Rise in the sense the difference in stress value before and after short pinning. Because every process is going to induce some stress into the component. It can be compressive or it can be tensile. So before short pinning, there is always going to be a certain stress profile on the component. And if there is a slight variation in process or the metallurgy or the raw material in between what the customer is doing in-house and what the supplier is doing, then there is going to be a difference in value. So the most important aspect is to focus on rise of compressive stress rather than the absolute value of compressive stress. So like we had discussed earlier in the first lecture, the first step is to do this measurement. So the tools required are here. I'll just briefly name them. It's the Allen gauge used to measure the arc height. You have got the Allen strip holders, and the fixture on which the holder goes. So first thing is obviously we have to look into the saturation curve. So here I'll just briefly refresh the memory. I won't go into much depth, or I won't go into much of the explanation. The saturation point is the most important aspect, the first step of the short pinning process. Basically, it is a point where we have achieved our required arc height, and by doubling this time, the change in the intensity is going to be within the 10% range. So basically now what we have achieved is we have achieved a stable curve exponentially. So irrespective of change in cycle time or increase in cycle time beyond this point, the deviation in arc height is going to be within that 10% band, which is allowable by the standards. So here you have to understand that the first point, the point T at which we achieve this saturation, is called the 100% coverage area point. And when we say 100, 150% or 200% coverage, we are just increasing the cycle time by that factor. So a 200% coverage, which I had shown earlier, frankly means the cycle time is equals to 2t if you refer to this diagram over here. If it says 150%, then it will be 1.5t and so on. So this is one of the typical graphs which we had plot. I won't go into much discussion because we had seen this earlier also. Now what we'll do is we'll first look into the pinning media, basically the quality control and the specifications required for short pinning media. Now here a lot of variety of media is used. You have got steel shots. Steel shots again have two categories: the cast steel shots and the cut wire shots. Then you have got the ceramic media. You have got glass beads. But for the sake of keeping the presentation compact, we'll focus on the steel shots, which is widely used in the industry. So basically almost all major international organizations have their standards. For automotive, mostly SAE standards are used. Then there are American military standards as well, applicable for the aerospace industry. And lastly, now with the experience, all OEMs have also developed their own standards, which is what you can say a mix and match of various standards coupled with their practical experience and requirements. So it's fine to follow either of the standards as long as both the parties agree to it mutually. So now why we are talking about the media quality? Because in short pinning, in my personal opinion, I would say the quality of shots play far more critical role even than the machine itself. Because the quality of shot pinning and the results that need to be achieved are directly related to the quality of shots. So even if the machine is working fine, if the quality of shots is poor, we are never going to achieve the desired results. Desired results in terms of the stresses that we want to generate. So that is why the most important point to focus during the process is the quality of shots. Now here I have just summarized a few standards. Now here again you can see there are two different standards. One is for the procurement of new shots, which is SAGA 444 standard, and then there is a different standard to check the quality of shots which are in process, meaning which are being used in the machine. So you need to take a sample from the machine and then analyze it based on this system. And again, like I said earlier, uh, any standard can be followed as long as it is validated by the customer. So now what we'll do is we'll see what are the quality parameters that need to be checked in terms of media. Now first here is basically the particle sieve analyzer. Now basically this is just a multi-deck vibro sieve. Each deck will have one wire size of wire mesh. The size, each size will represent a respective size as per the SI standards, and this size will be applicable to that particular shot size. So say for 0.6 to 0.7 mm shot size, there will be a particular set of sieve sizes that are mentioned in the standard. Now if the shot size changes, say we go to a higher shot size 0.8 to 0.9, so in that case again these sieves, the sizes of these sieves will change. Now what the standards say basically is you take roughly a sample of few grams, 100 grams by weight, you put it in this analyzer. Now here in the photo, firstly I'll clarify, the one on the left hand side is an automated machine. Basically it's a vibro sieve lab setup, and on the right basically it is a manual shaking type sieve which has to be operated by hand basically. So once you pour in the shots, the specific weight of shots, say 100 grams, the standard will suggest that each deck should have a certain amount of shots in terms of weight, and that weight shouldn't exceed. So this controls the quality of shots in terms of size. So for example, for say 0.6 to 0.7 mm, the standards might say that 5% by weight, the shot should be in the range of above 0.6 and below 0.7 mm. Then the next stage they will say is that 80% shot should be in the range of 0.55 to 0.6 mm, and so on. They'll define the percentage by weight. So first thing is you have to analyze the shots, see that they follow this particular pattern in terms of size distribution. If okay, then we'll go to the next stage. Now what the next stage basically is, typically the chemical composition that needs to be checked, the hardness needs to be checked by placing the shots on the resin mount, polishing it and checking in the hardness. Now once these two are okay, then we check the microstructure. If the microstructure is okay, then we go for the density and the visual inspection. The visual inspection basically is mainly for surface cracks or any other defects. Once the shots pass through these quality stages, they can be introduced in the machine, and the same needs to be followed whenever new shots are added to the machine and after a particular frequency for the shots which are being used in the machine. Okay, so now after the quality of shots, now we'll talk about the residual stresses and what the measuring techniques are. Now basically when we talk about residual stress, what we mean is stress which is present in the component or a material under its normal condition, when it is not under any external force or it is not constrained from anywhere. Now why do these stresses come? Because each process the component or the material goes through, each and every process is going to induce some type of stress into the component. It can either be a helpful stress, which is a compressive stress in our case, or it can be a harmful stress, which is a tensile stress. So every stress is going to generate every process is going to generate some stress in the component, and ultimately before shot peening, a component is going to have a particular stress profile. This stress profile again can vary based on the process, the metallurgy, and the chemical composition of the raw material as well. So I've just listed some origins of residual stresses basically. It's the same what we have discussed. It's like the processes like forging, drawing, extruding. Then you have got the microstructural changes, basically heat treatment, aging, maybe some superficial surface treatments are done. And then obviously heating, cooling, shrinking, all the factors are going to change the properties of the component or the material, which is going to induce some sort of stress into the component. So this again is a typical stress profile curve which we had discussed earlier. So I won't go into the depth, but this is what we have to achieve, a sort of profile, and the values of the stresses that are required to be generated will depend again on the customer standards, whatever is required by them. Now, here I have listed down a few points which are very important to keep in mind during the study of the compressive stresses. Firstly, basically the compressive stress, the maximum compressive stress is function of the material and metallurgy. It is not function of the process or the machine. We can induce only up to 60 to 70% of this compressive stresses in terms of the yield stress of the component. So the maximum stress basically is function of the material, the yield stress of the component, and not the process parameters. Where the process parameters come into picture is to optimize these results. So what the process parameters will do is, by manipulating them, we can achieve this desired stress. We cannot exceed this stress. We can achieve the desired depth of the stress, basically the depth of the layer or the thickness of the layer, and the desired stress profile which is required. Beyond this, the machine cannot exceed, or the more stress values cannot, the compressive stress values cannot be generated. Beyond a certain point, all the energy is wasted and plastic deformation will start. Okay, so I've just summarized a few stress measurement techniques over here. Now, first is the, what you can say is it's the most common method, which is the X-ray diffraction method. Now, this is a highly reliable method of measurement, but again, it is very expensive since the lab setup required for this is very expensive, and it is a destructive testing method for stresses where points are to be measured below the surface, basically the subsurface measurement. After that, you have got the Barkhausen noise test. This is a, what you can say, non-destructive testing method, but it will give you a numerical value which corresponds to a stress range. It won't give you an absolute stress value. And last one is the maps. Basically, in maps, again, we are measuring the stresses, but here it is measured in terms of the changes in magnetic behavior of the component, that is before and after short pinning. So these maps system, they need to be calibrized, or they need to be calibrated to each and every individual component. They won't give you an absolute value anytime. So this is a short description for the Barkhausen noise test. Basically, what Barkhausen noise test does is, we are generating noise signals within the magnetic field. The component is within the magnetic field, and the response to this magnetic field, basically in terms of changes in the amplitude of the noise signals, corresponds to certain values. These need to be calibrated, and these values will represent a number and indicate if we have achieved the desired stress level or not. So here, as you can see, basically if the amplitudes reduce by a certain number, these values need to be calibrated every time for each component. So this indicates increase in compressive stresses, and if the amplitude increases, means when compared to what you can say before short pinning component and after short pinning component, then it indicates increase in the tensile stresses. So in this setup, what needs to be done is, you have to create a chart first for each and every component. based on its corresponding stress values. So the stress values need to be measured first. Corresponding to that, you will get a particular number, and every time the number should be compared with the chart prepared. So this can be a good system for online inspection of parts, or ideally for segregation of mixed parts. Sometimes if a batch gets mixed, short pinned and not short pinned parts get mixed, then this is an ideal equipment to sort out the parts as well. The same can be done for with maps as well. In maps, the system is same overall, but instead of noise signal, we are detecting the changes in the magnetic field of the component. Okay, so now we'll briefly talk about the optimization of the process. So here, basically, I've just listed the cause and effect parameters. So what we are doing is we are impact generating kinetic energy and converting that kinetic energy into impact energy. So all the parameters that go into kinetic energy, like the velocity, the mass, the angle of impact, everything is going to affect the short pinning process. The effect areas will be obviously the coverage, depending on how much coverage we want. With the increase in intensity, the roughness is going to increase. Now this roughness can be reduced by dual short pinning. Sometimes two-stage short pinning is done to reduce the roughness of the component after short pinning. And obviously the changes to the microstructure and the micro hardness of the component. So what we have to do is basically we have to study each and every parameter during the process establishment stage and find the optimum balance between the cause and the effect, so as we get a balanced result, and at the same time we get the required stress profile as well. And now lastly, I'll just briefly go through a few of the typical problems related to the process which we have come across over a period of time. Now firstly, what happens is we start the process, establishing the process, but we are unable to achieve the arc height. Generally this happens when the arc height requirements are on the higher side. Now why this happens usually is, like I said, first you have to check the quality of shots. If the quality of shots do not match the standards, typically say there are the batch size is of correct SAE standard in terms of the size of shots, say 0.6 to 0.7 mm, but the distribution of shots in terms of weight is not correct. So maybe a low quality shot will have more undersized shots. So what is going to happen effectively is, although they are saying it that they are in a within given range, but still you are not going to achieve the results. So first thing is you have to check the quality of shots, and most importantly the size distribution of shots. Secondly, the hot spot position, the hot zone which we had discussed earlier, where the short pinning intensity is the highest. So the component should fall within this zone. And lastly, you have to confirm the correct shot flow rate. Now many a times what happens is some mechanical issues creep up into the system which increase the motor amperage or which increase the load on the motor. The users fail to, what you can say, catch this point, and they somehow assume that the short flow is increased and the short flow is correct. So here again you have to check for the correct current readings, that is before the shots are started, when the turbine is running at full RPM, and after the shots are started. Here there can be a lot of deviation in the range of 30 to 40% also in some cases. Then what happens is, the second point which we see usually is users are not able to achieve the saturation point. In the sense, the curve becomes highly unstable. You are achieving the required arc height, but the curve is not stabilizing. The moment you increase the time, the arc height is also increasing by more than 10%. So typically this happens when we are overpinning the component or setting the parameters way beyond the requirement. So what needs to be done basically is, first you have to reduce the speed of the turbine so the intensity reduces. Once the intensity reduces, the arc height will come within the range. And secondly, you increase the shot flow rate. Now, what happens is when you increase the shot flow rate and reduce the RPM, the strip gets covered in less time. So it has more probability of getting stabilized in given time. And lastly, you have to control the rotational speed of the component also. The change in rotational speed has an effect on basically achieving the saturation curve data. Then sometimes what happens, this is a very typical problem which we see, is that everything is going as per requirement. We have achieved the arc height, we have achieved the saturation curve, everything is set, cycle times are set correctly, coverage is set correctly, but even after that we are not getting the stress values. Now this again typically happens because of the inferior quality of shots. Now why this happens, or why shots are to be checked first, is because arc height is taken on a aluminium strip which is of spring steel. It is a soft material. So we are going to get the required arc height if the intensity, the RPM and the flow rate is correct. But when the component is introduced in the process, the hardness of the component plays a critical role. And to achieve the desired compressive stresses, the hardness of the shot should be greater than the hardness of the component. Then only it is going to create the micro dents required, and these micro dents eventually are going to generate the compressive stresses. So typically what happens is, if the hardness is not correct, or again like I said, the distribution of the shot size is not correct, you will get the arc height, but the stress analysis or the compressive stress won't be achieved. So you need to check for the shot hardness first. Secondly, like before, you have to check for the particle sieve analysis, and obviously the shot size is also which is the outcome of the sieve analysis. And lastly, what we'll discuss is basically there are also some errors in the X-ray measurement equipments. Now, what are these errors? Because the X-ray measurement machine or the X-ray diffraction equipment are not readily available everywhere. There are quite very few equipments, and not many people have ever operated this machine. So firstly, what you have to understand is there are various technologies of generating X-rays, and every equipment is going to have its own resolution and its own power. So these parameters and the other statistical parameters of the equipment should match. Means whatever the customer is using, your client is using, the supplier should also use a similar machine. Secondly, what you have to look is basically the preparation of part. For X-ray analysis, the part needs to be cut by say wire cut method. You need to electropolish the parts and ensure that no additional stresses are developed or stresses are relieved during this cutting operation. Thirdly, the orientation of part, the way it is kept on the machine, the way the angle at which the probe is pointing towards the part, and how it is measuring in terms of the direction and the direction of motion. So these also play a critical role in the results. Basically, there is going to be variation if these parameters change. And lastly, there is a very important factor that needs to be considered, because not many people go what you guys ask for this particular factor. It is the lambda correction factor. You can Google it and you'll find a lot of detail on this. Basically, it's what you can say, it's a topic of a complete different lecture talk. Lambda correction factor basically is the correction factor of that individual machine. Now, short X-ray machines have got some inbuilt data on which they calculate the given results. So every machine is going to have that different set of parameters and a different correction factor included in the calculations. So these parameters and this factor of both the machines, the machine being used by client and the machine being used by the end user, they should match. If they are not matching, there is going to be a change in, or there is going to be a variation in the results, because like I said, the actual stress induced are in the range of the difference value I'm talking about is in the range of 300 to 500 megapascals. So Even a small change can result in a deviation of around 60 to 70 megapascal, which means even though the process is correct, stresses are also correct, but only the values are showing differently because of different methodology is used. So this is one of the major factors that need to be taken into consideration. So with this, I end my topic, and I'm open to any questions now, which you people want to ask.
So Amit, thanks for a wonderful session. It was
Thank you.
short but very, very informative. So my name is Amol. I am from John Deere Tech Center, Pune.
Yes, sir.
One question is from the design perspective, what are like different specification if we like want to put it on a part? Like generally the design from the design perspective, it is uh, the main requirement is only having the compressive stress. But
Correct.
what are the other things which is important from putting it as a uh, like a specification point of view, which should be like very important on the print. Okay.
Yes,
So
like I said earlier, actually, when we talk about the stresses are more what you can say it's of a R&D part because it cannot be measured online during the process. So for the process to be reliable, you need to have number one the arc height. So what a design engineer is going to do is firstly is going to short pin few components, measure the stresses, test the component for their fatigue failure basically. At the particular point where they have got good results or the results that they want, they'll check what the corresponding arc height is. To this arc height, you are going to add some safety factor and then mention that arc height onto your drawings. So this is the first part. Second part which I have said is basically the coverage. Now what happens is at 100% point, the saturation point, you have got the 100% coverage, but as a design engineer you should add some again safety of factor over here. So if you have achieved your results at 100%, then you can definitely add a buffer and say 125% or 150% into the process. So even if there is any deviation, that extra cycle time is going to take care of the stresses, and at the same time the arc height is not going to increase because it is going to be within that 10% range. So these are the two major parameters.
okay, so what I understand is the value of compressive stress. Okay, either surface or subsurface. Second is the arc height, and third is the coverage. So these three are most important.
Correct.
Okay.
And obviously, the shots which we have used. So shots, you can directly mention it. You don't need to do any analysis over there.
Okay. Yeah. Thank you very much.
Thanks, Amit. We'll take some questions from our chat box.
Yes, yes, sir.
There is Manral who has asked about glass shot pinning and why
Yes.
it is done. Yeah.
Basically, again, it depends on the user's requirement. Now, a glass or ceramic beads, they are used like during the presentation I had said, sometimes dual stage, two-stage shot pinning is done. So in first stage, what happens is you do high intensity shot pinning. This creates the required stresses, but it also increases the roughness. So to mitigate that roughness, you do glass bead pinning or glass pinning over there. So the surface becomes less rough. Secondly, what happens is for delicate components, where the intensity requirement is very low, their steel shots cannot be used. And the readings cannot be taken on the element strip if steel shots are used because it is that small range window we are working on. So their glass beads need to be used.
Yeah. So thank you, Amit. There's another question from Mr. Ganpati.
Yeah.
He has a problem of shots stuck in the gear. How to prevent this?
Basically, sir, what is happening is the shot size is, I think, on the higher side. It needs to be reduced. Ideally, if you go through SAE standards, what they say is the shot size should be half or maybe 30-40% of the radius at the gear root of the gear basically. So if the short size is higher than that, then there is a problem of gears sticking in the tooth or whatever area that is being short peened. So the size needs to be reduced. We have to check the radiuses over there.
Yeah. The other question is how design engineers can calculate requirement of compressive residual stress and depth. Any thumb rule or standard reference, please?
No, there is no thumb rule for that. Like I said, what the design engineer has to do is they have to short pin the parts at various different intensities, correspondingly various different compressive stresses. You have to do fatigue testing, rig testing of the component, and at what parameter you have found your performance, the life which we are looking for, that needs to be then mentioned into the drawing, because like I said, short pinning is related to the metallurgy or the composition, material composition, and it's not related to the machine process. So for same arc height, same intensity, same coverage, same short size, if the two components are having different metallurgy, their performance is going to be different, or the stresses generated are going to be different. So it needs to be established for each and every component.
Yeah,
How to, how to
good evening,
ensure-
Amit. Sorry, Regis, to interrupt you. Suresh Kanoje here from John Deere.
Yes, sir.
This why I asked this question that generally there is I have read some literature which suggests that this compressive residual stresses should be 50 to 60% of the UTS value.
Correct.
That is the one which I have read somewhere. And as you
Yes.
suggested in today's talk that the maximum can be 50 to 60% of yield strength, right?
Correct. Yes.
So just a designer, I know there are so many studies what you have suggested, rig testing and all.
Correct.
But is there some thumb rule which is a proven thumb rule that okay, this can be a compressive residual stress minimum
No, sir.
requirement?
No, there is no such thumb rule. There are only guidelines.
Yeah, those guidelines. Sorry, yeah, I can say guidelines
Because,
also.
no,
Yeah.
because what happens when I say that you can induce compressive stresses in the, as much as 50 to 60% of the yield stress, but at the same time you have to look at the component geometry also, because
Okay.
maybe some geometry might get damaged. You will see plastic deformation in those areas, or maybe the
Right.
roughness increases, which is not desired. So even these factors need to be taken into consideration.
So I can come to the straight to the point. I have a component having 47 to 53 HRC hardness. It is a
Okay.
spring steel having 47 53 HRC hardness through hardened part. So
Okay.
is there any guideline that what should be the compressive stress if I want to increase the fatigue life, minimum compressive stress requirement?
No, sir. Like I said, there's no guideline for that, because how your component is going to be loaded or how it is going to work in the actual cycle is going to vary. So that is why you have to do individual testing of all the parts, the fatigue testing basically, and then only we can determine what are the values. And
so that one I think direction which you gave was that you can measure the initial compressive stresses, right? Whatever is there on the
exactly.
part, and then maybe as you suggested that 300 or 300 to 500 MPa rise, correct? That
Exactly.
one
Yes,
can
correct.
target.
Correct. Exactly.
Okay,
And
so that is the good I think direction, right? As such.
yes, so that will be a first step. Now, once you do that, you will
Yeah.
get the results, and from there you
Yeah.
will come to know what the consequent steps should be.
Correct.
Yeah,
So in general, can we increase? What is the maximum this MPa residual MPa rise can be there? Is it 300 to 500? Whatever you
No,
suggested.
like I said, we can induce say up to 60 to 70% of the yield stress. And what happens is this is the absolute value, and what you have to say where a component is before short pinning, because the short at that time, at that stage, it is going to have some stresses induced in it.
Exactly.
Yes, so
That's very practical and
match basically.
exactly. Okay.
Yeah.
Thanks a lot.
How to
Thanks a lot
ensure
for the
coverage of coverage in a gear? What fixtures is how to ensure coverage and what are the fixtures used? You have any idea?
For coverage, fixtures are not used. For coverage, what we do is basically we simply apply some luminescent powder, basically water-based powder. Let the component dry. you short pin it for the saturation time, the T point which we have achieved on the saturation curve. After that, you just take it into a dark room, check it under UV light. If the powder is removed entirely, then you have achieved your 100% coverage.
Yeah.
So what I was
Another,
asking basically, is there any particular way or orientation how the part is to be kept basically? I mean,
So
90 degree the
basically, the shots should
90
hit
degree the short indentation or
right angle. So whatever the surface you need to shot,
what angle?
the shot should hit perpendicular to that surface. So generally what happens is the components are kept
Okay.
straight so that they rotate along the axis. The angle of the blast wheel changes, or the nozzle, whatever we are using, that changes.
Okay. One more question I have regarding the first question about the glass or pinning.
Yes.
Please, when you use the glass sorts, it is harmful for the human life or something like? I mean, since it is glass, it can go inside. What care to be taken while doing the glass or pinning?
Yes, actually, using glass is a bit harmful because it can cause more damage compared to steel shots, and the dust is associated with tuberculosis. So basically, what needs to be done is you have to use a good
Yeah.
quality dust collector and make sure that operator doesn't work in that dusty environment.
yeah.
Okay.
Another question regarding shot
Okay.
quality.
Once we have done the steel shot.
Okay, Manral, once you
Yeah.
complete, please let me know. Yeah.
Yeah. My question was basically once you have done the steel short pinning and you got a particular level of compressive stress already increased in that. If you do
Yes.
after the glass short pinning, will there be further enhancement in the compressive stresses? If yes, up to what extent?
No, you won't. Second stage glass spinning won't give you more enhancement. What it will do is basically it will improve the surface roughness, because the
Okay.
intensity
Okay.
of glass spinning is going to be quite less compared to what we have achieved using steel shots.
Okay. There is another question regarding shot quality.
And also, yes,
Presence of slag is noticeable. Is it acceptable? If the shot
slag,
quality
which slag referring to?
regarding shot quality, he asks whether the presence of slag is noticeable, whether it is acceptable.
No, slag should never be present in the shots.
That's it's a logical, yeah. What
Yes,
could
yes.
be possible reason for high consumption of shots in process? That is one.
Basically, what happens if the hardness is low? If it is less than the hardness of the shots, the consumption is going to increase because the shots are just going to burst after hitting the component.
Yeah, Gadpiri, I will take your question. Maybe last we will take that image of shot ball struck. So we will just go with some few questions more. Some customers demand 200% coverage. Will it
Yes.
increase compressive stress beyond saturation? Will it
Yes.
help?
Yes, it increases the compressive stress.
Yeah, will it help in increase in fatigue life of components?
Yes, if the compressive stress is going to increase, so is the fatigue life going to increase. But within that given range, which is decided by the customer.
Yeah. So the question again is this: some customers demand 200% coverage. Will it increase compressive strains beyond saturation? That's the question. I think that you're not answered. Did you answer?
Yes, actually, like I said earlier, it is going to increase the compressive stress because, like I said, what the designer is going to do is he's going to add some factor of safety into the process. So what happens is the stress profile, the depth of the stress and the stress profile is going to change after the saturation point. So it is always helpful.
So Amit, Suresh here, maybe as you suggested that beyond saturation, there is hardly 10% maximum improvement we can expect. So
Correct.
can we
Yes.
say that this compressive stress improvement would be maybe of 10% max, right?
No, that it is not directly correlated.
Oh, okay.
Yes, it can be more also. Mostly we have found that it is on the higher side. It's not linear. because
Okay. Mhm.
from my personal experience, I'll say most of the results and most 90% of the things happen after saturation point and between the coverage point.
Okay, Suresh.
Yeah. Thank you.
Yeah, wait. There are a few more questions. Let other people also answer, answers. Sir, can you please let us know that how much there is increase in percentage of torque rating of automobile gearbox after short pinning? This is the
So it is
question.
difficult to comment like that because, like I said, it depends entirely on the design parameters. So actually, it is the other way around. What we have to do is how much percentage increase you want. Based on that, we have to do reverse calculations and see if what parameters need to be changed to achieve those results in terms of short
Uh,
pinning apart from other parameters.
Yeah.
Hello, sir.
Mr.
Gaurav here. Uh, Actually, I
Yes.
asked that question. Uh, so,
Okay.
uh, uh,
Gaurav from?
honestly, Gaurav from Divgi TTS Pune. Actually, we deal with in gear and gearbox.
Okay.
Okay.
So from your past experience, have you came across some studies like this?
Uh,
That
yes, actually, short pinning is done for that only to increase the performance of the gear. So
right.
I would I won't name the companies, but uh, typically, if you see one of the commercial vehicle manufacturers, they are, if they increase the mileage warranty of their transmission gearbox or the crown wheel pinions, the transmission elements, it is because they have introduced short pinning over there.
Yes.
Yes, or at the same time, there's increase in payload capacity of the machine of the vehicle. For the same model, you can say it is mainly because they have made certain changes and they have introduced short pinning as well.
Oh, okay, sir. Okay, sir. Sir, I have another question. Can I?
Uh,
Santosh
who's this?
from Tata.
Could you
Uh,
identify
Santosh
yourself?
from
so, sir, is there any correlation between HV value and the residual stress?
No, there is no such correlation.
Mm, okay, sir. Okay.
Yes, because short selection depends on the metallurgy, basically, and the results that you want.
Mhm. Okay, sir. Thank you.
Yeah,
Next one
can
is
we achieve, there's one question. Can we achieve residual stress in short blasting? They took trials and they achieved 0.4 mm arc height. Is it possible to skip short pinning?
Uh, you cannot skip short pinning, but what you have achieved is also correct because ultimately short blasting is sort of short pinning. But what is going to happen is you are not going to get a consistent result in terms of process parameters. And also, if you check all the components, the entire batch, the results are going to vary because in short blasting, some components are going to get hit by the shots at a preferred angle of 90 degrees. So there, that short pinning effect can be seen, but you're not going to get results because A, it is not going to be consistent, and B, although you are getting arc height, the energy actually is used to dislodge the scale and not to create the micro dents. And lastly, the hardness of shots. Generally, for shot blasting, such high hardness shots are never used.
Can you please identify yourself? Moto G5 Plus, 5S Plus. Who's this?
Hello.
Yeah,
Yes.
please. Who is this,
Hello.
Mister?
I'm Vaibhav Joshi
From?
Yes.
from Sanjay Auto,
Okay.
Thank
Aurangabad.
you. Thank you. Keep joining us. Yeah. There's Mr. Ganpati. You can now project your picture of shots getting stuck in your gear. He wants to have some more data, I mean, some more information about his problem. So I
I'll just
think he can now,
Thank
yeah,
you,
it's
sir.
a
Thank you. Thank, sir. Yes, sir.
yeah,
Thank
go
you,
ahead,
sir.
Mr.
Thank you for your
Ganpati.
opportunity. I will say,
Yeah,
I'm sharing, sir.
yeah, please. Go ahead, please.
Sir, I'm sharing, sir. Sir, first of all, we are doing an output shaft, sir, for short pinning.
You're
okay.
Ganpati, Mr. Ganpati from?
Sir, from Hyundai Motor Group, sir.
Hyundai, okay, good.
Hyundai motor.
Yes, sir. Tell me.
Actually, we are having a rotation table types of short pinning.
Okay.
That must be Korean machine, right?
Yes, sir. Korea is Shinto makes, sir.
Okay.
Shinto. Okay.
My mobile hangs, sir. 1 minute.
Yes.
We are using now cutway swords, sir. The
Okay.
size is 0.7 mm.
Okay.
That harness is 48 to 52 HRC.
Okay.
Our surface harness is HV is 820 HV specification.
Okay.
Actually, we have two issues, sir. One is short stacking in that all through available, sir. In that in between the stacking, I will share
Okay.
the mobile is my mobile is hanging, sir. Sir, can I
Oh,
share your personal number again photos?
yes, sure. I'll just type my number over here in the chat box.
I have solid number. I have.
Okay, yeah, then it's fine.
Okay, then I will
Now
take
here,
another questions. There are a few more questions I will take.
Santosh here from
Yeah.
Tata Hendrickson. Can I audible?
Who's this? Who's this?
This Santosh here from Tata Hendrickson.
Tata?
Hendrickson.
Just a moment. There are a few more questions. Let me take, because chat box people are, sending few questions. Let me take one or two and then you
Yes.
can talk. Yeah. What is the difference between NCA type strip and which is used where?
Basically the difference is in the thickness of the strip. So I'll just share the details. Just hold on a second. I'm not able to find that image over here, but basically the changes are in the thickness. So you have got N, A, and C. N strip is the thinnest strip. A strip is somewhere in middle, and C is beyond that. Wait, I'll just show you over here on the screen. Just hold on a second. Is this image visible?
Yes.
So basically, you have got difference in thickness. N is the thinnest, A is somewhere in between, and C is the thickest of the strip. And what happens is the usage depends on the intensity which is required. If the intensity is very low, then you have to use a thinner strip because you don't get a resolution. So for very low intensity, N strips are used, where typically in glass beads, N strip is used. A strip is where somewhere the requirement is in the middle, like for the automotive gears. And C strip is where very high intensity short pinning is done. So where A strips are going to fail because they are not going to bend beyond that, or they might get cracked also. So C strips typically, if you see, they are used in uh, connecting rods, and mostly into the what you can say the power generation sector or the railways and defense, where very high intensity and very hard forgings are used. Also in aerospace, where you have to do short pinning of titanium and other parts, there the intensities are so high that A strip just cannot sustain that much intensity.
Yeah. Is there any a lot of people want some thumb rules? There is another man. Any correlation of compressive stress at and arc height without doing any trial?
Uh, no, it is very hard to comment like that.
Yeah. Any relationship between percentage retained austenite and stress induced in component? What if we have 25% Ra in steel, which will short pinning will increase fatigue life of components? as compared to with less than 10% RA? It's a good question.
Sir, basically what happens is with higher percent of retained austenite, the bulging of gear occurs after short pinning. So it should be on the always on the lower side.
No, could you please repeat? I could not hear.
Basically, there is if the retained austenite is on the higher side,
Yeah,
there is gear bulging.
bulging. Yeah, bulging could happen.
Yes. So for that purpose, you need to have lower retained austenite into the component, and stress generated is going to remain same because it is not going to get affected, but the quality of the gear is definitely going to change after short pinning.
So after short pinning, I mean for short pinning, should short hardness be always higher than the part hardness, or can it be otherwise also in some cases?
No, it should always be higher because the purpose of short pinning is to create micro dents on
Indent,
the
dent. Right.
yes. So the dent cannot be
That
created
was
unless
explained.
the heating particle is harder than the base particle.
I think our ex-chairman, Mr. Sabnis, wants to ask one question.
Yes.
Sabnis, sir.
Yeah.
Please go ahead.
Thank you, Sandeep.
You are welcome, sir.
Amit, actually, lecture is as like last time. This also was very good lecture, very informative. I just want to ask you this topic as such is generally covering only ferrous and ferromagnetic materials, or it is applicable to non-ferrous as well?
It is applicable to non-ferrous also.
Because I'll tell you, I got a specific query from a non-ferrous industry manufacturing leaded brass components.
Okay.
Their components are failing because of, I mean, it is suspected it's because of stress corrosion cracking.
Correct.
So they want to check whether stresses are retained there and if that can be reduced, that stresses.
Short pinning can definitely help over there, sir. Because short pinning is used for non-ferrous materials also. It is as bigger field as the ferrous materials.
But all your standards will be will have to again develop or something like almond strip or all these things.
Yes, for every component they need to be developed, sir, if it is not readily available at the end user, at the client side, basically.
So, do you have any experience in non-ferrous industry?
We can help, sir. What I can say is I don't have any experience in non-ferrous industry, but the process remains the same. I have experience with the process. How it needs to be done, so that we can take care of, and what all parameters need to be changed or where we should start, those things I have with me.
Thanks,
yes.
Amit.
Thanks, Amit, for your nice, very informative lecture. A lot of people have asked a lot of questions and their queries. Unfortunately, because of paucity of time and I think before some confirmation, we could not gather many because I could not send it to many people and remind them. Yeah, generally we get around 100 people odd. So this time it was 67, 68, I think 70 something odd. So anyways, see, more the merrier because they get more knowledge about the process, and a lot of questions can be answered, and the answers of the question again improve knowledge of people.
Correct.
So I want a lot of people to join it. Yeah, it's a cycle.
Yes.
And of course, once the knowledge is given, the manufacturing people also have a lot of information about the things. Yeah. So thank you very much, Amit, for your nice lecture. In spite of our last moment, this thing, it was very nice. And of course, we will have another one. Yeah, we will have one more for short blasting at your will. And so when you are free. So thank you very much, and thank you very much all the participants. Yeah,
hello,
anybody
sir.
there wants? Yeah. This?
Yeah. Hello, sir. Can I just take a moment before closing
the
session?
Sure.
Yeah, my name is Ram, sir, from Duty TTS. Hello.
Yes, sir.
Yeah. Basically, Mr. Amit Aradhe, thank you very much, because I had initial discussion almost 10 years back with your father regarding our short pinning requirement. but afterwards there was no much of requirement. So basically, we did not give much attention on this particular. Now we
Yeah, I think Amit, he lost net connection. But in the meantime, Ganpati has sent you the picture.
Yes,
If
yes,
you
sir.
can see this, yeah.
Yes.
So this is what the shot he got into this.
Basically, what is happening is the shot diameter needs to be reduced, or that area needs to be protected.
Yeah, it's a swaging gear. Swage gear. Ganpati? Yeah. So I think, could you answer this?
Yes, like I said, basically, what you can say is the diameter is on the higher side compared to the clearance between the profile.
Yeah.
So
So he
there,
needs
either
to,
yes, you need to reduce the diameter, or if short pinning is not required there, you can mask that area also.
yeah. Okay, thank you. Thank you all participants for joining so late. And thank you, Amit, again, once again.
Congratulations, because within a one day notice, we could have, within a 1 day notice, we can have the more than 65 people. So it is creditable.
Thank you very much.
Thank you very much, sir, for your kind guidance. So, thank you very much. Thank you very much, all the participants, and we take leave. So, good night to all. We will take again the next Saturday. We'll meet on 3rd of July, and again on 10th of July, again on 17th of July. So we'll keep meeting till at least August 10th. Thank you very much, and good night to all. Signing off from here, Mumbai ASM India chapter. Bye.
Bye.
Okay.